Hello and welcome to today's daily Leetcode challenge. We'll be solving question 1584. I'll be going through my thought process as I come up with the solution. And then at the end of the video, stick around to see me compare the solution that I got to the solution of others. And yeah, let's begin. Question 1584, min cost to connect all points. All right, so you're given an array of points representing integer coordinates of some points on a 2D plane, where points I, x, y, where the point of index I is x, y. The cost of connecting all points is the Manhattan distance between absolute value of xi minus xj plus yi minus yj, where absolute value 1 denotes the absolute value of val. Okay, so there's Euclidean distance, there's Manhattan distance, measured a bit differently. Return the minimum cost to make all points connect. All points are connected if there's exactly one simple path between any two points. Okay, and as the example, we're given a graph of points and an example of how to connect them. All right, well, so there's a couple of more examples. There are a lot of points, 1,000, but not a significant amount. So maybe we can iteratively go through all the different combination of connections, links between the points. Actually, edges. Edges would be the correct term. And let's see. Okay, well, how would I approach this? Well, I want to start thinking of this as a number of different islands that I have to connect. And the island problem always brings me to union find, so I'm right away thinking about the union find algorithm that I'll probably have to use, and maybe a slight modification, because in union find, what we would be doing essentially is just figuring out if and how to connect these 2 points until there's only one big island, right? And that's actually what we're doing first. We're maybe connecting this to, we're starting off with 5 islands, and then we're connecting these two, making 4 islands, and less until we have one big island. Well, the problem though is I don't know, like I know which one to connect this to. I know for this to connect to here. I know for this to connect to here. Basically the minimum Manhattan distance, right? I always have to find what is the minimal Manhattan distance for each one of these points. But what if I have a point out here that would have another neighbor, let's say here, right? If this point right here had another neighbor here, then I couldn't just I couldn't find the next smallest Manhattan distance from this point to another point, because I would find its neighbor that's right here, and those two would be each other's neighbors. Those two islands, these two big islands, would never connect. And so for that, I'm thinking that this is where I would have to use like an iterative approach to look over all the different connections that I could possibly make. And that's why I think that maybe looking at all of the edges, the possible edges, would help me, right? And so what I'm coming to is I have a union find mechanism to group all of these islands into one, but then I also need some sort of min heap of all the different edges to find the which edges could be prioritizingly joined or made real by connecting those two dots. And let's see. So yeah, that's pretty much it. I would have to modify the union find a little bit from my usual approach, but with that, let's begin. Union find for me is always just a list where I in range of L. Let's define L as the length of points. Let's define a find point if UF point is equal to P, or return P, meaning that I found its parent, and this is not parent, this is point. Else, return find my parent, which would be union find of parent. Then we have to define a union of P1 and P2. I'm going to call the mega parents of these U1 find P1 and U2 find P2. If I don't make sure I have to have this yet. I'm going to now call union find of U1 to U2. And that's it. And that is the basic union find algorithm. I'll probably end up having to modify it later, but let's stick around with this for now. What now? Well, now we need a way of looking over all the possible distances between all the different combinations of points. So I'm going to have a distances array that has let's also have something here called the M distance, P1, P2. This is going to be the distance calculation. So the Manhattan distance, return the absolute value of P1, 0 minus P2, 0, plus absolute value of P1, 1, minus P2, 1. The Manhattan distance is going to be used here to calculate for now for I in range L. Would it be L minus 1? Yes, L minus 1. For J in range I plus 1 till L. This is negative 1. These are my 2 points. I'm going to find the distance to be the M dist of points I and points J. Now, to have this be sorted, I could sort this right away, but I'm actually going to just heap push distances. Heap push onto the distances a tuple that is going to be dist I and J. Let's print distances to see that my distances are sorted. Actually, it's not going to be a lot, right? It's not going to make a lot of sense. Local variable. Sorry, what? Oh, I for I in range. Sweet, that's a heap. Just a bit rushing a bit through this, but I have this heap, and now basically while distances, I'm going to say dist M dist is going to be equal to 0, and I'm going to now say that heap pop distances, and this is going to be edge. edge is going to be my weight, P1 and P2, I1 and I2. And now, what do I need? Now I have a weight. Okay, now I think I have to modify this. So if union of I1 and I2 is true, then, and this is where I would actually modify this. So if U1 is equal to U2, I would return false because there's no way I'm adding two that are already of the same, and else return true. Union of this is true, then I would simply add to my mdist plus equals weight. And is that it? I would iterate through all of my possible combinations of the distances, distances heap, and what I would add it to. Let's see, dist. Yep, looks about right. I'm a bit of a rush, so let's see if this works right away. Sweet. Okay, thank God. Again, almost didn't complete the daily challenge, but now that I'm here, I'm gonna just quickly also summarize what I'm doing here. Union find, as all of you may probably already know, is just an algorithm to merge islands together. A big group of islands initially start off as just islands pointing at themselves, and in this union find array, the index of any element is itself the number. Like for example, 0 is 0, and the value at that index is the parent of that node. So index of the node is the node itself. Value of the index is the parent. And so grouping them, unioning them, means just overriding one of its values to another. So here, the parent of union find becomes U2. And so you could actually visualize this as like a root structure, where the top parent eventually becomes this U2, and all of the little points and intersections where the roots split is just another point. And so what I'm doing here, though, is using the heap implemented as a min heap in Python to sort all of my possible edges, which are just all of these little ones. And there are a lot of little edges. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9. I forget what the actual value is. I think it's n times n minus 1. But there are a lot of these edges, which is probably where I'm getting penalized for my memory, or the amount of data I'm using, memory I'm using. But essentially what I'm doing here is creating this distance array heap, and then just looking at the minimum distance, prioritizing the minimum distance each time. And when I'm able to union them, that means that these two islands are yet not connected. Then I just union them, and this would already union them here, and apply the weight of that weight of that edge to my minimum distance, and returning the minimum distance. And that's pretty much it. Cool walkthrough. And wow, we are very, 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 very bad. However, wow, that is terrible. Is there another? Whoa, I did not think this video would be long. Get distance. Okay, so let me maybe look through at least one of them. I will not have that much time, but okay. Yeah, I just really just want to compare, see what I'm doing here. The penalization here is for certain the number of edges I'm creating. I'm thinking, is there a better approach? I might end up just doing a different video on where this algorithm gets talked about, because it doesn't seem like they're using union find or heap. And so yeah, I'm not seeing my approach anywhere here. Oh, distance min heap. Min heap pop. This is definitely the same thing that they're doing here for I in range distance. This is exactly what they're doing. Distance of P1, P2, and the point itself. Yeah, guys, I probably will just cover the better solution in another video. For now, I find this pretty intuitive. I really like union find, so I probably just gravitated towards using that rather than the best approach. And heap is very intuitive. It's always prioritizing the smallest value. Since this is a tuple, it's prioritizing it by the distance. And so it seems like the best way, but obviously it's not by the runtime wise. So I'd still say, I don't know, on interviews, would they care if it's drastically slower? Probably. But what am I? An interview? Not an interview mode. So yeah, let me clean this up a bit. See, maybe the runtime there was just a bit slow, because maybe people are submitting their solutions. And no, not significantly slower, faster. Anyway, yeah, I will still recommend this just because of its intuitiveness and its feel, but I'll probably end up making a video where I talk about the better approach later on. So thank you for watching. See you in tomorrow's video. Bye.